For homework 13, we're going to take a look at buckling analysis of thin-walled cones in cylinders subjected to external pressure. First, we're going to take a look at analytical solutions for both cylinders and cones that are unstiffened. We're going to take a look at a method for stiffened cylinders and stiffened cones. And we're going to take a look at experimental results for unstiffened and stiffened cones. Probably in part B, we'll look at the abacus analysis for linear eigenbuckling, which is a linear perturbation approach for determining initial buckling loads. And there's some things we have to watch out for in that. But we'll take a look at the sections in the theory and the user's manual for that. And probably at the end of that, then we'll take a look at the comparison to the experimental results. Now, I had the nice fortune to have a project related to cone buckling, and from that I learned a lot about shells. Typically do a lot of fatigue testing and analysis of structures, but this was a very fun project, and there's a paper related to that I'll point out, and I'll put this in the download section of my website and on the integrity section on the box for our students in class. So this paper was published, as of this video, about 10 years ago in 2007 on the buckling of stiffened thin-walled truncated cones subjected to external pressure. And I have a section of my website devoted to this research as well, and we'll take a look at that. But if we scroll through it, the application of the cone was pretty unique. Of course, you might think of cones in aircraft or in missiles or something like that. But this particular cone was proposed to be used in a nuclear fusion reactor called the Z-pinch, inertial fusion energy reactor. And it was proposed at Sandia National Labs to generate electricity from nuclear fusion. So here, down in the central portion, is the location of the cone. And in that section, there's actually two cones. One is nested inside the other, but in between the two cones, there's a lot of high vacuum. There's a very high vacuum, so there would be a tendency for the inner cone to buckle. And these are transmission lines because they transmit electricity. So you take the electricity and you send it through the inner cone. Down at the tip of the cone, it's flattened, it's a truncated cone. Down at the tip, in between the two cones where they nest, there's a little space, and there's tungsten or wires. You send enough electricity through it, and the wires explode, and they impact a deuterium pellet where this load is at. And in that process, you start a nuclear fusion reaction. I'm not a nuclear physicist, so I can't tell you any of the details about how all that works, but it's basically kind of a hydrogen explosion or reaction. And in the course of that, this thing explodes in this giant tank. There are jets of what they call flibe. It's a fluoride type liquid metal. The energy and the blast is absorbed by these flibe jets, and the heat is carried away and heats up water, and then the water goes and turns a turbine. That was the idea. There's more information that you can find out about that from another article I'll make available. It's called The Development Path for the Z-pinch IFE, and this was written primarily by Craig Olson at Sandia National Labs. Goes into the details of what it takes to do all of this. Well, in the course of this, they wanted to know if they could, what the buckling pressure of these cones would be, how close their analytical and finite element methods would be for this. Buckling problems are very imperfection sensitive. And if they could integrate any stiffeners in the design of these cones, then maybe they can increase that buckling pressure. So, if you pull a hard vacuum, you're around 14.7 or so psi, and of a differential pressure, depending on what what's going on the other side of that if you're exposed to atmosphere on one side. So it could be as high as that. And of course they'd want to maintain some kind of safety margin. Now, if one of these cones did buckle, then these things could make contact here, and then you basically short out this process by which you're putting electricity through these cones to make that those tungsten wires explode on that deuterium pellet. So that's kind of the background. I thought it was kind of interesting. And in part of this, we're going to take a look at some equations that are in this paper. Matt Turgeon was my sponsor at Sandia National Labs, also a master student of mine, and Varun Nare was a student of mine a few years back as well. So here's basically what one of these cones look like, and there's some nomenclature that we'll get into, but it has a large diameter on this side, a smaller diameter on this side. And to test these, I put them in a pressure tank with this air pressure acting this way on the cone surface, and then it would cause this to buckle into kind of a lobe shape once the critical buckling pressure was reached. And then to get the stiffening, we put stiffening rings on here. I had these adhered with structural epoxy. This cone is a very thin cone, about 25 thousandths of an inch. To put that in perspective, a typical soda can is around 4 or 5 thousandths of an inch thick. And I guess these are somewhere around 2 feet tall, maybe a little bit shorter. Okay, so we apply the air pressure, and then you get some buckling. The more stiffening rings you have in the right spots, you have an increase in pressure. And all of this data has been tabulated in one of these charts that I have in here for the experimental, and of course what we'll take a look at is the analytical and finite element results. And I have some nice videos of everything that happens here. So there's some that have multiple stiffening rings, and you increase your buckling pressure, and if they're in the right spot, you get a nice buckling pressure. These were in kilopascals. But anyway, at this point, I want to talk a little bit about first analytical formula for buckling of cylinders, and then how to change it to buckling of cones, then how to transform that to something we can use for buckling of stiffened conical shells. So we're going to start off with, in this paper, let me get to the right spot, taking a look at a formula called the David Taylor model basin formula for determining the pressure of cylindrical shells. Now this was developed, I think, sometime in the 40s. We can take a look at the reference. But I believe it was related to submarine design. So you have a conical shell. You want to know what the buckling pressure is going to be, because you don't want to go below that crush depth for your submarine or whatever. But a lot of this was based on some of the work by von Mises. Von Mises not only did his famous stress equation for equivalent stresses, but also did a lot of other things in elasticity and plasticity and buckling a shell. So all around, he was a fairly famous mechanics type person. Let me get on to the next page here. And this is the equation for determining the critical buckling pressure of a cylinder. So it's 2.42 times the modulus of elasticity, 1 minus nu squared to 3/4. You have T over D, the thickness over the diameter, and H over D, the height over the diameter, that appear in this expression. So let's write that down, and we'll talk a little bit about it. Alright, so we have this lateral pressure acting on the cylinder, and E and nu, again, the modulus of elasticity and Poisson ratio. The other terms in here are the geometric dimensions. And you know, if you think about it, it makes sense. If you decrease the thickness, if you increase the diameter, you're going to get a lower buckling load, and if you expand the height, you get some effect with that as well. So all these terms in here kind of make sense. Now, if you were to apply stiffening rings to this cone, Let's talk about that situation. See if I can draw a cylinder here. Sometimes it's hard to draw a straight line on this thing. And if you have these cylinders such that it can cut into the lobe that forms, so if this was just an unsupported cylinder, it would probably buckle something like this in different lobes around the circumference, and you can even calculate the number of lobes that should form. But if you were to be able to cut this with a stiffening ring that goes around here, you're effectively reducing the height. So your new height would be in this formula, and the new lobe that would form would be down in this section or up in this section. So you can take and have a stiffened cylinder have a shorter effective height, and then you can increase the critical buckling load based on how many stiffening rings you have and what the height is that you have in your stiffened cone at effective height. A stiffened cylinder, rather. Now, there's a method of being able to take this cylinder and transform it into a cone, or rather take the cone and transform it into the cylinder. And that approach, let's use a different color. And that approach would use an effective diameter of the cone. So if you have a cone and the top is R1 for the radius and the bottom is R2, maybe it's a truncated cone. Let's draw it as a truncated cone. Well, then you can find an average radius and an average diameter. And you can use that in this equation, again with the wall thickness and the height of the cone instead of the height of the cylinder. Well, there's an issue with using this in that way, and that is it depends on the angle of this cone as to how good this formula is. Of course, if there were no angle to it at all, if it was straight down, it would be a cylinder and it would work perfectly. But the tighter this angle is, this apex of the cone tends to act like a natural stiffener to that cone. And so we can express something called the taper ratio for the cone as psi equal to 1 minus R1 over R2. Of course, if you have that taper ratio of 1, that means R1 vanishes compared to R2. Let me fix this. This should be R2 up here. It should be R1 down on the bottom. If you have R1 over R2 such that R1 vanishes, then you have a taper ratio of 1. If you have a perfect cylinder, you have a taper ratio of 0. And so there's a correction factor that you can apply. And there were some tests done by another famous cone person, Side, here. They came up with this solution based on a taper ratio, a correction factor. So you have a correction factor that you can apply to this that can be, up to a little over 1.2 times the cylinder buckling pressure, depending on this taper ratio. Now, The cones that I tested had a taper ratio of about 0.8, so it was way up here in this region, a little bit over 1.2 for the correction ratio. And the correction ratio can be written then in terms of the taper angle and the radii in terms of this formula. Let me go ahead and write that down on the next page. Alright, so we have our formula for the equivalent cylinder based on the definitions of the cones. And so that's this formula right here that I tried to write down. And the angle alpha is the cone half angle. So if you were to extend this to the apex of the cone, that's this angle right here. And then finally, the estimated buckling pressure for the cone incorporates this formula plus this function of psi that we just talked about, depending on what the taper ratio is. Okay, so that's how you can get an analytical solution for the cone. Now, for my cone, let's see if I can find the dimensions here. I had a height of about 550 millimeters, and R1 of 50 and R2 of 250 millimeters. Cone angle of 20 degrees, which give me a taper ratio of 0.8 and a thickness of 0.635 millimeters. So this is pretty thin steel. It's much less than a millimeter thick. So I went through and I calculated those up. And then the other thing that I did then was to put different stiffening rings in here in different locations. So the stiffening rings effectively constrain the lobe formation in these different zones. Now each of these zones, here we have 1, 2, 3, 4 zones in which buckling can occur. Each of those zones could have a critical buckling pressure based on the same method of using the stiffened cylindrical shell formula with a taper ratio correction in it. So there's a taper ratio for this section and so forth. And the minimum of all of these is the one that controls the buckling process. Well, let me get down to the results here. There's some nice pictures, and I'll show some videos of the test in the second video when we finally compare the analytical and the experimental solutions. But here you have some lobes that form in the stiffened shell, in between the stiffening rings. And there's some finite element results as well that we'll talk about. But down in this table is a table of the kilopascals of the experimental buckling pressure and the finite element and the analytical approach. So the analytical approach for no stiffening rings gave 75.7 kilopascals. Finite element solution we'll see gives about 88.9, and the experimental result is about 58.3. Now, the thickness of these cones is something that the buckling pressure is very sensitive to. If you have a small deviation in thickness, you can get a large deviation in buckling pressure, as you can observe from that formula. And I calculated it somewhere, but I think it was if you were within 0.2 millimeters of your nominal shell thickness, that can give you a deviation of about 7 to 8% in critical buckling pressure. So the fact that the experimental results are lower than the finite element and analytical solutions is not terribly unexpected. And this ratio of the experimental and finite element solutions, or the experimental analytical solution, can give you what's called a knockdown factor that you would want to use in your design. So the knockdown factors based on these tests were between 0.73 and 0.77. And that was fairly consistent for these different stiffening ring configurations. Now I used A, B, C, D, E, and F stiffening ring configurations, and those are outlined in the paper as well. In this table right here. Okay, so these are the Z locations for the 5, 4, 3, 2, and 1 stiffening ring configurations. Of course, we also had a 0 stiffening ring as well. All right. So I think that'll give enough of a background. Let me do one more thing. I'm going to try to provide you with a couple of spreadsheets where I did these calculations, and you can take a look at it. So this is the equivalent cylinder. This is a 5 stiffener ring configuration. So if we have 5 stiffening rings, we basically have 6 places in which the buckles can form. And taking the modulus of elasticity, Poisson's ratio, the angle, R1 and R2, and the thickness, and all these different terms, and with the correction term thrown in, this is the pascals of pressure and the psi of pressure that we get out of this. Of course, the one that's the smallest is the one that's going to control, and in this case it was the one near the top of the cylinder where the is the widest section, so away from the tip of the cone. And for the 5 stiffening ring configuration, it was calculated to be about 28 psi for the critical buckling load. What is that, about 193 kilopascals. Okay, so that's a pretty good pressure. So I'll give you one of these spreadsheets, and you can kind of see where these terms come from and play around with that if you'd like. Alright, so with that background, what I want to do then is to have a part B video where we load in one of these files into Abacus. We perform this linear perturbation analysis for eigenbuckling, and we get the results out of that.